Morning, team.
Morning.
Everybody having a nice lazy Monday morning? Let's see. Good to see your face, Ebold. How you been doing? I haven't talked to you for a long time.
Not much. Just finished one of my classes, the finals and everything.
That's
So
awesome.
now it's just pretty much this class.
Good. Let's get this done, huh? Are you still working quite a little and all that?
This is gonna be my last week of work, and after I'm gonna start packing, moving to Klamath Falls, OIT.
Okay. Wow, that is huge. That is huge. Are you excited about that?
Yeah, I'm super excited. Taking classes in person. Yeah.
Yeah, that's super wonderful. So let's see. I do want to take a quick second this morning. I always like to make sure, just kind of play around with the projects a little bit. And you guys turned all those in, and I graded those and put them back into my open math, I think on Friday. But let's just take a quick second and talk about a couple of things. Sharing a screen, and then let's get after it. Looks like the iPad's kind of sleepy too. A little sleepy. And we are looking at something today called the phase plane, which is kind of a way to solve a second order differential equation, or not a second order, a system, since chapter 5 is really all about systems. Let's see, my iPad seems to be sleeping, so we're gonna stop sharing. Try that one more time. See if doing it a second time makes it wake up faster. It did. Okay. So I just wanted to show you a couple of things. I mean, lots of people had success with this, after hints and so forth. And so, but I just want to show you a couple of kind of methods that are sort of neat that maybe you didn't do just because of the end. It's kind of neat to see that. So I mentioned at the time that given that this was the original differential equation we built, we said, hey, if you multiplied by a and squared both sides, then you would have this, which looks a little better. And of course, that's not. You'd have this, but of course, that's where you get stuck. So I gave you the hint that taking the derivative of both sides, which is a rather surprising idea, was a rather good idea. And so I just want to show you one other thing that was an option that some people didn't notice. But if I say, okay, a is just a constant, then the derivative of junk squared means the junk comes down front and the junk stays unchanged. But unfortunately, you have to multiply by the derivative of the junk, which is a derivative of a second derivative is the third derivative. And then on the other side, the derivative of 1 is nothing. And then the derivative of junk squared again is 2 times the junk times the derivative of the junk. And then that would be terrible as well, except for the fact that you notice that, well, hey, look, they both have one of those. So I can just divide those away. And they both have a 2. I can divide those away. And so all I really end up with is a squared y triple prime equals y single prime. And it's then for the first time that you realize, hey, that actually looks like something I can solve. And so people then typically, at least what I saw when people turned in, is they did this with a Laplace transform, and that's awesome. So I won't go through that business, but you end up with the Laplace transform. I'm going from memory here, so I'm a little worried I'm going to blow this, but I think it was a squared, a cubed s over a squared s squared minus 1. I think that's, if you didn't screw up the algebra, that's kind of what you got. But here's something cool that maybe you didn't notice that you could have done that would have saved you some trouble, which is just also kind of neat to think about. Well, notice you have derivatives on both sides, and we have already kind of agreed that the whole purpose of this class is you're stuck with something, as we started with here, that, you know, had a derivative in it. And then inevitably you're kind of thinking, well, I wish that wasn't there. And since the opposite of a derivative is an integral, then take integrals. Well, what would happen if you took the integral of both sides of this? I mean, those are derivatives, right? Well, actually, that isn't very hard because integrals take away derivatives. And so if I do that, I'm going to get a squared, and then one of those derivatives goes away. And when I take the integral of the derivative on the other side, that derivative goes away. And if I take the Laplace transform of that, it's going to be far less trouble. Or perhaps you take the approach of thinking of this as a second order differential equation, and you like the guessing technique. So you say, oh, look, my auxiliary equation has an a squared in front of the y double prime. There's nothing in front of the y prime. So there's sort of no a's, and then there's a minus 1. And so let's see, and those are r's right here. So that's an r squared, and then there are no r's, and then there's a 1. And so I'm solving that auxiliary. Maybe you're taking that approach. Again, I just want you to think about all this for a second. So you end up with r squared equals 1 over a squared, which means r equals plus or minus 1 over a. And since that was your r, and we knew that our y's were equal to e raised to whatever that power is, 1 over a x or 1 over a t, since it's plus or minus, then you've got those kind of two answers, and that kind of takes you out of the water. It's like, oh, cool. So that's the form the answer takes. And of course, we got to, put C1s and C2s in front of that and figure those out based on our initial conditions and so forth. And so that was kind of cool. One other thing I want to show you, and so, a lot of people kind of eventually got their way to that with some hints and hopefully some discussion from other people. But I do want to show you one kind of cool thing, and I kind of hinted at this in class, but let's just take a quick look at it because it's just kind of fun to see. And let's go kind of slow. This is sort of the end of your calculus knowledge, so it's kind of good to employ it a little bit. But what if you're sitting right here and you said, let's let u be equal to y prime? In other words, what you're really doing is kind of taking the integral of y prime. So you're saying u is sort of like one dimension back. I don't know if you remember my discussion in Math 251 and 252, but really a derivative is changing a dimension of things. Maybe you remember, if you have the volume of a cone is 4/3 pi r cubed, and you take the derivative of that, then you get, wait, I'm drawing a blank, yeah, cubed. 4/3 pi r cubed is the volume of a sphere. And so that's a three-dimensional. If you're asking for the volume of something, you're asking for, the space it fills. A three-dimensional answer is what you're getting right there. But if you take the derivative of that, 3 times 4/3 becomes 4. Pi is just a constant, and then this reduces by 1. Well, it turns out that's the area. In other words, when you took the derivative, which was a volume, you actually got an area. So it actually took you down a dimension. So it's almost like, really beautiful and deep and powerful, and almost mystical way to think of derivatives and integrals is dimension changes. And so if I let u be y prime, it's kind of like, okay, well, then what do I got? Well, now that's just u prime instead of y double prime. And then this is 1 over a square root of 1 plus, well, y prime is u, that's just u squared. And so now I just took it all down a dimension. Now it's like, hey, it used to be a second order differential equation. Well, now it's not. And so, you know, what follows from that? Again, I just think this is kind of a neat way to look at it. So notice our first approach was, I guess you might say, really surprisingly brilliant idea, you know, to take a derivative that gets us out of this mess. And so now this is our second brilliant idea, which is, I don't know, taking it down a dimension. Now we can't just do that. In other words, you can't just change something without, right? I mean, something changed here, right? Now we had volume before, but now we have area. So it's like, I'm not solving the same problem anymore. But the cool thing about this is, what if you realize that this u prime is really du dx or du dt, depending on how you want to think about it. Let's see, we're talking about a cable. So, I mean, I guess I'll use x's instead of t's here. That's what u prime means. And so then if I'm staring at this, what might occur to you is, hey, that's, in the language of this class, that is a separable differential equation. So if I leave du on this side and I have the square, since I can divide by all of that, and I leave the 1 over a on this side and then multiply by dx, look, that's not a hard, I can sort of get rid of that derivative, if you will. And so the integral on the right side is the one you volunteer for because it's easy. The one on the left, though, is horrible. You may at least vaguely recognize, hey, that's kind of Pythagorean theorem down there on the bottom. And we had to make trig substitutions to make that work. And not only is this a trig substitution, but it's a horrible trig substitution. Or you say, yeah, we spent a lot of time with that kind of stuff. And we talked about the idea that, you know, these things are hard to find, just like Laplace transforms are hard to find. So you make a table and, you know, you figure them all at once. Or you could, you know, so you just look this up in a table, or you get on a site like Wolfram Alpha or COI Math and say, what's the integral of 1 over the square root of 1 plus x squared? And again, I'm going from memory here, so I hope I'm right. But I think the answer to that was the natural log of this plus this. I think that's what it was. And so again, this feels really like, is this doing anything? This feels fruitless. I'm not really sure what's happening here. Remember that when you take an integral, you need a plus c, and that is very profound. And so it's really plus c on both sides. So if I collect it on the right side, that's fine. And then I get rid of natural log, of course, by raising both sides to the e power. And so now I have e raised to that wonderful power. And you might recognize, hey, that's the same as e to the 1 over ax times e to the c, since I added exponents. And this is just like a, you know, still a constant. So let's give it a new name for a constant. So it's kind of a better way to write it. A nicer way to kind of write this gigantic square root sign is just to, you know, call this C1 e to the 1 over ax. And of course that's looking, you know, this is looking correct, but you know, you might think, well, there's supposed to be a negative too. And so, you know, where's that coming from? I don't really know what's going on here. But again, some really interesting algebra is required. So if you're sitting here staring at this, you might think, well, that was all true and that's really good, but now I sort of feel stuck. Like I have all these u's, and so, you know, I could like go back and put y prime in for you, but look back a little bit, like clear back to the start. If you look back at this business right here, you know, notice we have right there the square root of 1 plus y prime squared, or 1 plus u squared, and notice that's equal to a times y double prime. In other words, this thing right here, that's a y double prime, and that plus u is really plus y prime, and that equals c1 e to the 1 over a x. And so if you recognize that substitution, we just took it back to the world that, you know, really existed, the y prime world. And notice now, hey, look, I'm comfortable now. Wow, okay, this is a second order. This is a second order differential equation, and I know how to solve those, and I won't take it from there. But But interestingly, if you solve that, what's kind of fascinating about it, and again, part of the reason I'm showing you this because it's really cool, and I'm very anxious that all of you actually own this beautiful curve and can make this catenary formula yourself. Thomas and Cheyenne both spent a little extra credit time kind of surfing around, looking at, who invented this stuff and where did it come from, and when was it discovered, and who was the person that first proved it wasn't a parabola, and those are cool too. Thank you guys for taking the time to do that. It was interesting. But you may notice what's kind of cool is this is a second order differential equation, and it's actually non-homogeneous, which is kind of neat, which means there's going to be a y1 answer that's kind of the homogeneous answer. So where I think of this as all being equal to 0. And interestingly, that homogeneous answer is actually the one that's going to produce the e to the negative 1 over ax answer that we need, which is kind of cool. And then when you go after the, non-homogeneous answer, based on the fact that it's e to the junk, then you're going to say, okay, well, my guess is a times e to the junk, whatever that is. Oops, that was a positive. And so, actually, I'll elaborate just a hair more. Your homogeneous answer actually has kind of this. It actually produces both a positive and a negative answer. If I remember right, and I think that's true. But then this one happens to be kind of repeated down there in the non-homogeneous answer. And so it's just kind of neat that, there's sort of two brilliant methods, and there may be more, that actually produce the same exact set of answers. And so now that we kind of own this problem, one of the things I've spent quite a bit of time with, just because I kind of find practical physics interesting, but I spent a whole bunch of time kind of figuring out sort of the principles behind how a zip line works. And just to at least alert you to the kind of the neatness of this problem. If I hang a cable between these 2 points in the tree, and of course the cable's inevitably going to sag a little bit. So the fact that I know now that that's kind of hang as a catenary curve, of course, in the case of a zip line, the question is, if I took off from that top tree and went down to the bottom tree, am I going to come into that bottom tree at like 50 miles an hour and just smash the tree and die? So, you might say, okay, well, that's fine as long as your system has like a brake in it. And so then you design that in, and maybe the brake's automatic, or maybe it's controlled by the person on the zip line. But what would be far better and sort of safer is if somebody came in, reached this minimum point right down here, and of course that'd be kind of like their maximum speed, but then they actually burned that speed off as they kind of climbed back uphill for the last part of this. And in my picture, you can probably tell you would die from this one. Like that's not enough of a climb to kind of fix all that. So as you slide from a physics perspective down that cable, you're losing some of your energy thanks to friction and so forth. And so the question is, could I then come back to the bottom tree with enough of my energy lost in friction and actually come into the tree at some sort of a reasonable speed that you can control and make people have fun, so to speak. And so what we did here, given the fact that we understand that this catenary equation, we actually have the equation that models that curve now. Of course, that's one element. There's actually still quite a bit of work to do in that. That's a very difficult problem still. And what it really comes down to, and I'll just kind of leave it at this, but is to say, okay, well, let's just say you just hook that up really randomly, and you knew that like the height change. Just quickly move all this down. You knew the height change from here to here was, I don't know, 80 feet, whatever. That was 80 feet. And then you knew that the distance change between here was say 1,200 feet. And you could do Pythagorean theorem to figure out what the straight line distance was on that. And of course, then the cable would just need to be longer. So, and then of course, the longer you made the cable, the more the sag would be in it and so forth. But if I did that just out of curiosity, and I'll just leave you with this interesting problem for you to think about yourself. I am going to do the Pythagorean theorem really quick on that. Pythagorean theorem, I got 12. You might be surprised by this, but I got 1,202.6 feet. Notice it's only 2.6 feet longer because 1,200 is so much bigger than 80. My drawing isn't to scale. That hypotenuse isn't that much longer. So based on the fact that you'd have to have a cable that was at least 1,202.6 feet long, and you'd never be able to stretch that, it would tear the trees out of the ground. Let's say that you made this cable like 1,300 feet long. Does it make sense that you ought to be able to figure out then exactly the exact equation for that cable? And again, all that you need to know about the cable is A. There's only one constant for that. But of course, the hard part of this is the bottom of the cable is not in the middle. It's not halfway between that 1,200. And so, if you think of your XY axis as being like this, that's not an easy problem. And of course, the most important part of this is just how much is the cable actually going to sag? Because that's kind of the point I was trying to get across, in the sense that if somebody came sliding down this cable, somebody comes sliding down this cable and reaches right here, what you really want to know is, how much do they have to climb back up, and, will that dissipate their energy sufficiently with the friction loss so that they'll come in at a reasonable speed. And so, and of course, the bigger question is not, just pick 1,300 out of the air and then hope it works. The better picture would be, what length cable should you be using? Like, could you actually design the right cable length, hook it up, and then just know it would actually bring people in at kind of the right speed? So anyway, that's just the extension, the practical side of this. And of course, there's less playful versions of this, since we're hanging electrical cables in the air all the time through towns and so forth. You got to make sure you put the right length cable up so it doesn't sag down so low that people can hit it with cars and things of that nature. So anywho, that's kind of fun. Any, I don't know, thoughts or questions or anything about that project that you either want to say or is bothering you or anything before we tackle the phase plane? Last section. So this is not hard. So let's just kind of wade into a little bit. So I'm just going to kind of start off with an example that's kind of cool in the end, but let's say you have this, it still deals with systems. As I said, that's what all of chapter 5 is really dealing with, is systems of equations. And so what if I said, one of them is, I got an example here that I must have made up in the past, and hopefully it's a good one. And then a second one that is an X prime. This is what makes it a system. And so this looks like what we've been studying in this section. You're a little happy to see, if you will, on the other side that there's no derivatives over there. In other words, you have y prime equals and there's no x primes on the other side. But the fact that there's kind of x's and y's, there's so many of them, this is kind of hard to solve. And then we said, what did we say recently? You know, one method to solve this was that operator method, was that 5.2, where we change y prime to being dy, in other words, derivative of y. And so we can solve that system in this way. But I want to show you kind of a visual way to solve this. And it's actually going back to the start of this class when we looked at graphs of what these things look like, since what these really are is equations that tell you slopes. In other words, if I said, you know, we're at the point, I'm just curious, if I said I'm at the point, you know, x is 2 and y is 3, and I'm sort of, you know, thinking what's going on at that point 2, 3. Well, notice you can plug 2 and 3 into this and actually come up with the y slope. But notice in this case, it's not dy dx, it's dy dt. So I don't know, just for the heck of it, let's do that. So if I plug that in, that'd be 4 minus 40 minus 6 plus 80. So I got y prime, or dy dt, is 38. And what happens with x prime? Well, I'd have x prime or dx dt. And if I put in 2 for x and 3 for y, what do I get? 2 minus 9 minus 12 plus 6. I got negative 13. The question I have for you is, like, what do those numbers mean? Somebody want to take a stab at that?
The initial rate that those the two variables y and x are changing, depending on what we're talking about. Maybe it's like a concentration change, but
It's the initial slope of our two solution curves.
Yeah, and it's specific to y and x. And so to keep it simple, if I just thought of it as literally speed, the y speed is 38. And so we don't know what our units are. Are they meters? Are they feet? Are they miles? We don't know what our time is. It's seconds or minutes or whatever, but let's just say it's feet per second or something like that. Then dy dt basically means it's going vertically. Its vertical change of speed is, say, 38 feet per second. And its x speed is actually negative. So notice that one was positive, so I aimed it up. Whereas its x speed was like 3 times smaller than that. Like if I'm to draw this to scale, 39 and 13 would be 3 times smaller. So it's about a third. And it's going left. And so that's negative 13 feet per second. Again, there's no such thing as negative numbers. Negative is a direction. 13 feet per second is 13 feet per second. It's just a question of where you're actually going. And for those of you that have spent a little bit of time studying vectors, if you moved that vector up here so that it was head to tail, then that's actually your sort of final speed, which I could Pythagorean theorem my way to. The square root of 38 squared plus 13 squared is 40.2 approximately. So it's like 40.2 feet per second. And you could even find the angle that that was at by using second tangent and so forth. Yeah, I'm in degree mode, baby. I'll do it real quick. Second tangent of 13 divided by 38. Notice I'm not even putting the negative signs in there, and I got 18.9 degrees. And so that angle right there is approximately 18.9 degrees. And so notice that's what this is telling us is I picked a random point. It's almost like you have, I mean, think of it like this. You have a storm, you know, there's a storm. And so the winds are swirling around everywhere and you see trees moving around and everything is kind of moving. And, you know, you could just pick one point as you look out the window and say, what's happening right over there? Well, we just did that. We picked the point 2, 3 out there in the storm. And what did we see? You know, because this gives us a y prime and an x prime, it actually tells us the speed or the rate of change. It doesn't have to literally be a speed. It could be how quickly the chlorine, something is changing in chlorination or something, as I think Ben or David pointed out. But basically I could say, well, yeah, that point in space right now actually has a direction. There's like a little arrow there. And so that's why this is, kind of back to the start of this class where we talked about a graph. So, I mean, I could kind of go to the point 2, 3 now, and draw my, little vector sitting right there. But notice it has a direction. That's really the only difference. Way at the start of this class, we said, hey, look, we found the slope. And so we drew the line, but you see how the line has an arrow in it now? Because it basically means particles of dust that are in that area, or think of it as a hurricane because it's more fun. Like if there was a cow in that area, boom, going to be flying in that direction. So it's got a direction to it. Now we could go to a different point and get a totally different type of an answer, right? So just for the fun of it, what if I went out to the point 5, -1? You do that really quick. I just want you to have a really good feel of what this means. Like, what would its arrow look like? How long is its vector? This vector was 40.2. It's 40 long because that's a reflection of its speed, and the magnitude is 40, but the direction in vector language is roughly 19 degrees from vertical anyway. But what happens at 5,1? Can you punch that in really quick? And is that arrow going to be pointing really similarly? Or is that arrow going to be pointing off in a completely different direction? I'm doing this with you because I was just making this up. And I'm concerned I'll make a mistake, so we're all going to agree on this. Did you get 15.7? So the previous one had a speed of 40, whereas this one over here is way slower. It's like a third slower, and it's in a totally different direction. So, if I was to draw it accurately, it would have to be a lot shorter. So you see the idea here? It's like, wow, that's quite a storm. If you're at this point over here, you're being blown kind of up and to the left, and it's 40 feet per second. That's what's happening to those dust particles. But then I go over to 5, -1. The storm is swirling so wildly that second one is 15.7 feet per second, but it's 26.6 degrees from horizontal. I mean, this is the idea behind vector addition, where you draw them head to tail. You're being blown 7 in one way, 14 in another. And so if I draw those head to tail, then my kind of resultant vector has a magnitude, we say, of 15.7 and a direction. There's magnitude and direction to vectors. It's force in a direction. So the 26.6 is the direction, 15.7 is the magnitude. And so, wow, that's really interesting. And so, you know, what would this storm look like if I finished the graph? Does that make sense? If I kept doing this for all the other points, what would I really see? And of course, you know, the idea is, well, that's cool. I wonder what that would look like, but I got to get the arrows drawn kind of the right direction and the right size. And, you know, I just did 2 of them and it took quite a bit of time. And so is there some way I could do this faster? And so this is where a phase plane kind of comes in. So what does this really look like? Well, since we said this top one up here was really dy dt, and this one was really dx dt, does it make sense if you divided them? If you took dy dt and you divided it by dx dt, as you know, you multiply fractions by flipping the denominator and multiplying it upside down. So you multiply by the reciprocal, and interestingly, those cancel, and so you get dy dx. So if I chose to divide these two, then I would basically say that dy dx is equal to, well, those two equations divided by each other. The y equation, x squared minus 20x minus 2y plus 80. And that would be divided by the x prime equation, which was x minus y squared minus 4y plus 6. And this is what we did clear back in chapter, I don't know, like 1.2 or something like that. In other words, that's what y prime used to be when y prime meant dy dx. In other words, this is now telling you just the slope. Notice there's no speed anymore. It's not relative to time anymore. This is just a slope equation. And that's what we went into. We used to graph that, right? We used to be able to make a direction field, which was just a bunch of slopes by kind of plugging that in. And so that's kind of interesting. And so fortunately, graphing this, if I graph this, which I can graph using the same tools we used earlier in this class, then I can actually see, well, what we started to make for ourselves here kind of in slow motion. I can see the whole thing. I can graph the whole thing. Now I'm not going to get arrows. I'm going to have to determine the arrows myself, but I'm just going to get lines. I'm going to get slopes, but I'll have to add my arrows to them, which is what turns it from a direction field into a phase plane. And as I said, what's so powerful about this is the system of equations, and this is one of the huge things that, I don't know, physicists and engineers kind of recognized, is that you can break, to make sense of crazy behavior, you can break it into what's happening in the y direction and what's happening in the x direction separately, and just worry about vertical and horizontal. And in that way, you can kind of know what's going on. And so let's see what this looks like. So I don't really see that I have a choice but to go back to GeoGebra. Let's see, I'll show you what I showed you earlier in this class. I'm going to bring this back up again. I think it was this. I posted, it looks like it's 1.3, not 1.2. But 1.3 was where we did direction fields. And I showed you a Desmos version, which wasn't all that great. And I think the one we ended up using mostly was this GeoGebra version right here. I actually don't remember these other two. I don't know, let's try this one first. Control click. So Again, this was kind of an app that somebody made inside of GeoGebra. It's made from GeoGebra, but this is actually an adaptation that somebody made in it. And you may remember, this is what we did. We came in here and we typed, and notice it says f prime of xy. In other words, the slope is found. And then we said things like, okay, well, what if the slope was 2x minus y or something like that? And that created the slope field. That created, and again, do you see that? In other words, if I pick the point x is 1, y is 1, let's think about the point 1, 1. Well, if you put x is 1 in there and y is 1, you get 2 minus 1, which is 1. Oh, the slope at the point 1, 1 is 1. Well, if I go to the point 1, 1, look at that, the slope is 1. And I can increase the density of that, so I kind of see what's going on. And we played around with the fact that, remember we did a project where there was like this dividing line, like right there, it's like it's a line, but everything above that sort of has a parabola look, and everything below that sort of has some exponential look. And we, began this class figuring that out. But what we're trying to do is say, well, what if that is equal to some, complicated fraction? Now, what I'm a little worried about here, I actually don't know the answer to this, is will this accept something so gigantic? So dy dx is sitting there, and now I need to type x squared minus 20x minus 2y over 8 plus 80 divided by so forth. So I'm going to see if I can type all that in. I actually played with this quickly the other day, and I thought, gosh, I don't know if I can see all of that. So I'm typing this in, everything is looking great. X squared minus 20x minus 2y plus 80. And here's where I'm kind of not liking it, because notice it ran out of room and I can't see it. And there's nothing, I can't see any place where I can actually see what I'm typing now. So I think I said plus 80 parenthesis, hit division sign, start a new parenthesis, x minus, oh good, it moved, x minus y, so it is working. Minus y squared minus 4y plus equals plus 6. Close the parenthesis, hit enter. So I wish I could see all of that. I can see it right here. So yeah, notice I didn't. Actually, notice what it wrote. It's like it divided them. It's kind of like if I said, 5 halves. If I told you, hey, the fraction's 5 halves, and you put it into a computer, but then it divided it. 5 divided by 2 is 2 1/2. It's kind of like, I think that's what it did. I'm not happy about that. I wish it had just left it alone, because now I'm staring at that going, is that what I typed? I can't really see it.
Looks like you need to go back and add a parenthesis after the 80.
Yeah. Now I did that at the time. I put
Yeah,
those
but
in,
then it didn't accept it.
but you're right. It's like it didn't accept it. So yeah, I'm a little, I don't like that I can't see it. It's not happy. Not making me happy. Okay, there we go. Now I'm double checking, is that what I 80 x minus y squared minus 4y plus 6. Okay, good. So we have this, if you will, direction field now. So first of all, stare at our first point, the point 2, 3. I'm a little worried to do this, but let's go to the point 2, 3. It seemed like we could type this, I'm just going from memory here, but it seems like one of you figured out we could just type this instead of just guessing at it. So
maybe just double clicking on the point and you can type it in.
That's what it was. It was double clicking. Thank you. And I think that says that in the directions down below. Remember, this kind of goes crazy, and that's one of the advantages to some of the other methods. But remember, where they went crazy is when it got vertical. And so notice if you're cruising along this to the right with x getting bigger and bigger and bigger, and suddenly it gets vertical. And when it gets vertical, that's kind of where it freaks out. But the point is, what slope do you see right there? Well, a second ago, didn't we say that was a vertical of 38 and a horizontal of -13? So it was like 38/13, which is roughly -3. Well, notice, yeah, doesn't that slope there look like it's about -3? Doesn't it seem reasonable? Maybe it's better just to have this off. Go to the point 5, 1. I got my cursor, 5, -1. It's right there. And when we were there, it was a rise of 7 and a run of 14. That's a slope of positive 1/2. Do those lines in that vicinity, notice we don't have a line right on that point, but do the lines in that vicinity appear to have a slope of 1/2? Let's see what happens if I turn this one on, and thank you, Ben, for remembering that. I go to the 0.5, -1. So yeah, that didn't like that either. But notice right there, the slope does look like about positive 1/2. That's what we got. And so the point is, this is working. It created this direction field. That's kind of fun. Now, what I want to do is analyze this a little more deeply with you. Let's see. I'm going to take it out a notch, take it out to, I don't know, -20. I'm not sure how far to take it out. I'm going to go out sort of 4 times further away. Instead of 5s, I'm going to go 20s. What I'd like you to notice is, do you see some kind of cool, interesting spots? And again, think of this as a hurricane, and there's just winds blowing every which direction. Everything is really swirling around. Can you see the wind patterns and so forth? Can you see them flying around? And do you notice that there's a point right here that seems really fascinating? Do you agree with that? And there's another one over here that seems really fascinating. It's almost like, right there is where the actual tornado formed. You know what I'm saying? Like, for the most part, stuff was just sort of blowing around. And again, I don't have any arrows here. I don't really know what direction all of this is going yet. We're going to talk about that in a minute. But you can see this is exactly something you would need to study if you were going to be a weather forecaster. And this is the kind of thing you've probably seen even on kind of a, storm report kind of a thing, that they show these kind of Doppler radars where they, show the hurricane spinning like this. And so you have all these lines, but we kind of need arrows on them to show what direction it's going. I'm teaching. Ops is at the door. So, if this was weather, does it make sense? Like, that point right there is where there is actually a hurricane. Now, what I can't tell is it spinning clockwise or counterclockwise? Which way is it spinning right there? But those have arrows on them in this situation. Do you understand that? Because we're talking about speeds. Although we typed in here dy dx, which is only giving us slopes, that came from a system of differential equations that had x's, y's, and t's. And so the t's are actually what add the arrows to this. And so it'd be kind of cool to know, is this spinning around? And so there's a hurricane over here at point, 15.2, and that's some town, on a map. This is a huge map of an area of Louisiana or something like that. And so it appears we have sort of 2 twisters forming here. And, of course, I'd want to know what the length of those lines were, right? Because those would be speeds. How many miles per hour is it over there? And so every one of these little angled lines, and notice they're not drawing them different lengths here. But every one of these lines will represent kind of a speed and a direction. And then, I don't know, do you see any other points that are kind of interesting? So over here, it looks like everything is kind of, pretty uniform. It's like real straight here. It's coming down, gets straight, and then it sort of curves over here. But this looks interesting to me too. Do you agree with that? Like at the point, looks like about 5.2 maybe. Can't really tell. It's like, that's kind of weird too. So, and then the other thing I'm thinking is, now that I see there's kind of action over here and this all looks the same, I'm wondering if is there anything more to the right that I should know about? So I'm looking at X max and thinking, what if I went out, I don't know, further? I'm going to go out to maybe 40, and then I don't really need to see as far left as I did. So I'm just going to take that back to 10. Is there anything out there that I didn't see? I don't know, maybe 40 is not enough. 60. I don't really think I see anything different. And I kind of lost some of what I had before. So now I'm going to kind of try to hone in on what I had a minute ago, and so I can see it a little more clearly. Is that a good idea? Notice how, and this is kind of good that this is happening, and notice the window that I chose just now. It's like, it's kind of terrible. I can't really see at all. So now I'm kind of thinking I should punt. take it back to what I had before. That's pretty good. Maybe I can leave it right there. I'm the kind of person that just messes with stuff, so. So I'm just rolling the mouse here and I'm kind of just trying to see. Now, what I'd really like to do, and I'm going to do this in kind of a janky way, is what I'd really like to do is be able to copy this and bring it onto my screen so I can write on it. Since I didn't do this directly on my iPad, but I can do something a little creative here and at least take a picture of it. So this won't come in as kind of nice as it. No, that's actually pretty decent. I think I can live with that. Hopefully it'll focus. Share screen again. So I can bring in a photo that I just took. Let's see, is this going to work? Yeah, it's decent. I can live with that. I can really see it. So let's see, just to kind of highlight this, I'm thinking, seems like red will stand out really good. I'm thinking that is a really interesting point, and maybe right over there is a really interesting point. The idea is those are places I'd like to know something about. The other thing, the other way to think about this is maybe like gravitational field. In other words, you're flying through space. Space is an easier way to think about it, but really it's just the concept of a gravitational field. And, you know, again, the idea is like, I don't know if this is the case yet, but let's say that this is swirling. I guess that would be counterclockwise. Oops. This is swirling counterclockwise. And so you're kind of cruising along this way. And notice if you kind of over here, then you kind of might be in the orbit and just kind of orbit around. But notice if you're a little lower, you see how those kind of didn't make it and then they just took off this way. You see the concept? I mean, it's gravitationally the one that was right here ended up getting caught in an orbit around that sun or whatever that is gravitationally, whereas the one right below it kind of didn't get caught and it disappeared. And then for that reason, doesn't this point also look kind of interesting? Like I don't really understand what's going on there, but I see another one of those kind of right here where my cursor happens to be pointing accidentally, maybe right there. I mean, those points are particularly interesting in that phase plane. And again, phase plane just means we need some arrows on this. But let's take a second to kind of figure out what direction all this is happening. And then we're going to go back and kind of look at those points because those points would be really important to understand. And so let's just pick a point. Let's pick the point. I want to see something kind of, how about 4, -2? Now we just did this. Actually, let's do this for the ones we just did a second ago. We did 2, 3, right? Which is right there. And so right there, we knew the arrow was going that way. And what that means is kind of cool is all the other ones around it are doing the same thing. And then we went to the point 5, -1, which is about right here. And it was going in this direction.
Are those swirly points perhaps where the slope is equal to 0?
Yeah. Yeah, that's exactly right. And we're going to get into that.
Okay. I didn't read the chapter for this one, so I just wanted to get.
Well, that's good to know. Yeah, the slopes, where the slopes are 0, that's kind of where things freak out. And so that's exactly how we're going to kind of, that's the point of analysis we're going to use here. So that shows some.
Is that called a critical point then?
Yeah, that's exactly right. So there's, in my mind,
So
yeah, you saw that on the review. In my point, if I go back and kind of now that I've made more than one point, these points right here seem particularly important, right? I mean, there's other random points. I can go any place I want. But those points seem particularly important. If I could know where those were ahead of time, since, you know, again, if you think of this as weather, that would be really cool. Now, let's go up to this point that appears to be like, would you agree that point looks like 15.3 approximately, this point up here? Looks like the point 15.3. But let's just go, I don't know, somewhere nearby, like I don't know, right there. That's the point 14.6. Can you tell, can you do the math to tell if this is an arrow going this way or is an arrow going this way? Because that's going to tell us what's happening around that 15.3. Is that a counterclockwise rotation or a hurricane that's happening around that critical point? Or is it a clockwise rotation? So, and again, that's what we just did a second ago. That isn't rocket science. However, I'd like you to think a little more. Could you do this a little faster? Do we have to do everything? Think about this. Do we have to do everything we just did to figure out which of those two arrows I drew is the right one? That was back up here. Remember all the trouble we went to. Could I do that faster? Well, notice one is going right. One's going right, one's going left. Could you use, what could you do in the two formulas that we just had for dy dt and dx dt? What could you do to figure out whether it's right or left? I mean, do I have to know both right, left, and up and down? I just picked right and left. I didn't have to pick right and left. I could have picked up, down. But doesn't left mean dx dt is negative, whereas dx dt over here would be positive? That'd be enough. As I said, it doesn't have to be dx dt, it could be dy dt. dy dt, if it was up, would be positive, and so that would match the right one here, and then the left one is going down, so then dy dt would be negative. So I could do this with either one of them, but notice you could just check dx dt, and that'd be it. Is it positive or is it negative at the point 14? What do we say we're at? 14.6. dx dt was the x minus, so it's x minus y squared, so it's x minus y squared minus 4 times y plus 6. 14 minus 6 squared minus 24 plus 6. I don't really care what the number is. I got negative 40, but what I'm paying attention to is that. Aha, negative. So now can I go up here and determine what's happening up there in terms of the phase plane, in terms of adding arrows to it and so forth? Does it make sense that I can now say that this, if you will, everything around here, and you can check all the other points if you want, but again, you're talking, there's connection, like what's happening at one point is very similar to what's happening at the next point. Does that make sense? I mean, both of these two lines right here are close to the same. They're not the same, but they're close to the same, right? So what's happening to you is very similar to what's happening to your neighbor. Therefore, just picking that one point right there, I know everything in this whole picture is actually swirling around this. And so I can go over here and look at arrows heading this way. I can see those, way out here. There's still all of these points I seem to be looking at are like, seem to be caught in the gravitational field. All of these are creating, if you will, a hurricane rotating around that way. But can you see if you get out far enough, some things escape? What happens to this point out here? Did I point that left correctly? Yes, I did. But does that particle of air, does that cow flying around in the hurricane, does it actually stay in the hurricane? Notice the answer is no. I mean, you can see the lines kind of going like this. It's like that one's actually escaping. Do you see that that comes over here and actually matches what's happening in that blue one? So like in this way, I can actually kind of go through this whole thing and I can kind of see what's happening with all these arrows. So then I look back at, remember this arrow that we drew in there, and I think, okay, well, what happens with these guys over here? Well, they're spinning around and going this way. And so these guys are coming over here and going this way. These guys are going that way. So it's like, you know, all of these arrows are working their way this way. Are you getting the feel of this? And so that kind of means that all of these over here are also going around. So it's like both of these, if you will, hurricanes are clockwise. Oh, that's not true. This one over here was counterclockwise, whereas this one over here is actually clockwise, isn't it? So they weren't the same. Do you notice I didn't find very many? I only have 3 arrows in this that I know the direction of. And yet I kind of know what's going on here now. Now, again, can you see the critical point here is really important, because these that came by above it are kind of swinging in over here, and it looks like they're going to go up and kind of get caught in the orbit of this up here potentially. But there are some down here that are actually going the other direction. So it's like right below that point. Did you see this arrow over here was going left? Like all of these are going left. And so isn't that weird? Look at this, that point right there. The ones above it are working their way to the right. The ones below it are working their way to the left. You see how this is this point right here is what your book calls a really critical point to know. For the most part, you know, all of these dudes up here, they're all acting the same. Everybody's working their way to the right, working their way to the right. But all of a sudden right here, you're right here and you go below that, and all of a sudden they're working their way to the left. Does that same thing happen over here? Like what's going on with that one? Let's see, I got all these arrows coming in this direction. Oh yeah, look right below it. This arrow's going this way. Same thing's happening. It's like these are peeling off and going that direction. So it's kind of interesting. Like some of these are coming in like right here. And if they're a little high, then they spin off that way. If they're a little low, then they kind of go down here and potentially get caught in this vortex over here. And so, yeah, I can kind of see, can you see that now? This one is going down, whereas the one over here is going up. And so it's almost like that point is like a force field, like nobody wants to touch it. It's like, you know, 2 negative ends of a magnet. Like you go toward it, and it's like, it doesn't want to go there. It like wants to veer away from it. It won't go there. Notice it doesn't create rotational. Like over here, we see this is going up, this is going right, this is going down, this is going left. That wants to rotate. Do you see that? Whereas do you notice over here, this does not want to do that? Like this is going down, but then when it gets over here, it isn't going left, which would cause a rotation. It's actually going right. Like these are smashing into each other. And so those are different types of critical points. Do you see what I'm saying? One causes like circular rotation, and the other one doesn't seem to cause that. But it appears, now that I kind of threw in the arrows to create this phase plane, that these points are really important. All 4 of these are critical points, and I need to kind of know where those are, because those are having a huge effect on what's happening in this system, right? So that's a phase plane. Technology can draw those for us. I haven't investigated this, but I honestly, given where we are in technology, like, isn't there, maybe you Google search this while we're sitting here talking and we'll improve this, but it'd be kind of nice if we found a website that would produce the arrows for us, like rather than have to go in here. But I think it's, even if we did, then great, and let's use that. But even if you don't, isn't it kind of cool to see that you can generate those yourself?
It's a very entropic one.
Say that again.
It's a very entropic phase plane.
What do you mean? I know what entropy means. I think that's what you're saying, but explain that to other people.
Well, there's 2 spots that reflect each other perfectly, basically.
Got it. Yeah, so the fact that, there's two of them that appear to be, and I kind of like to think of these, I was trying to just have sort of a playful understanding of this, but these feel planetary. These have gravitational pulls that cause orbiting, if you will, maybe like a black hole. They're like sucking things in. I should just say a planet. I mean, they're planetary. They cause rotation around them, whereas these don't. They seem to repel things. Both of these are repelling, and I didn't really finish this with the other one, but this one over here is going down. And, these are all going up. And so this is turning and going off that direction. And so this one's going up. So it's important to see that the two that don't have circles are not causing rotation. Those are not causing orbit. They're repellent. So it's kind of like the two circular ones are attractant. I'm making these words up. They're sort of attractant, whereas the other two are repellent or something. I don't, is that an important distinction? Is that something I want to know? But the main thing I want to look at now, which David hinted at, is, how do you find these? It'd be kind of cool to be able to locate them. And so notice you can kind of stare at the graph and take an estimate as to what you think those ordered pairs are. Like what? I mean, for instance, this one down here, doesn't that look to be at the point 7, -6 or something, like right around 7, -6? Probably isn't perfectly 7, -6, but it's right around there. So let's turn our attention to that. This graph appears to have 4 critical points. And I say appears because remember that there could be one out at 5097, right? I mean, I didn't make my graph big enough. There's some that are further out there that I didn't see, or maybe there's some that are sort of microscopic and I didn't notice those. And so is there some algebraic way we could locate these? Well, notice even these lines that I drew right here, like, didn't we ultimately just say that, right below this, it's going this way, up here, it's going that way, over on the right of it, it's going down, on the left of it, it's going up. Well, notice those are vertical and horizontal slopes, right? That's kind of what's happening. I mean, if you get right down to that point, what's kind of weird and chaotic is it's horizontal. So I'm just looking at these two. It's horizontal, whereas one is actually horizontally negative, horizontally positive. They're both the same. I mean, they're both horizontal, but one is positive and one is negative. And then right in the middle, does it make sense? It'd be like kind of 0. It'd be, well, they're both 0. I mean, that's the thing that's kind of weird is this is, let's see, how do I say this? Let's just leave it simple. This is basically working its way to dx dt being 0 because it's horizontal right there. But then also notice, isn't dy dt also 0? Like it's also vertical right there. Like right at that point, the horizontal slope is 0 and the vertical slope is 0. And then what happens down at this one? Does it behave the same? Well, the answer is yeah. It behaves exactly the same. Horizontal slope is 0, vertical slope. Well, the vertical slope isn't 0. The vertical slope is actually infinite, isn't it? Well, that gives rise to, how do you find these? Well, when find where dx dt equals 0 and dy dt equals 0. Whoops. Both, not just one. Why not just one? Look back at the graph. How come not just one of them? Well, what do you notice over here? Based on our picture, I don't know if I can figure that out. Is that, I think that's going up over there. I'm not sure. Is that going up or down? But at the slope, the vertical slope is infinite, right? but the horizontal slope isn't infinite, so that's not a critical point. So I'm not interested in just one of them being 0. Look over here. Hey, look, that's 0. Oops. Look, that slope is 0. What's happening? This slope is 0. Thinks I'm selecting the picture. But you see the logic that it's got to be both. At these critical points, it's actually both of them are equal to 0. Okay, well, let's go figure those out. So let's go do the math on that. Let's go back to the original 2 equations and copy them. There's our 2 equations. I need both of those to be equal to 0. Stare at this for a second. Do you understand that if I look just at this right here, there'd be all kinds of x's and y's that would make this equal to 0. But the problem is whatever x's and y's I choose up here to make this equal to 0, they've also got to go down here and make that equal to 0. So let's try to do that. So how do I make x squared minus 20x minus 2y plus 80 equal to 0, and simultaneously x minus y squared minus 4y plus 6 equal to 0? How do I do that? You should algebraically have an answer to that. You should have something that you can say about that. Again, aren't I solving a system of equations? But notice it doesn't have any derivatives in it. It's not as ugly as it was before. You can't solve 2 equations, 2 unknowns. Well, keep in mind, actually, we'll go back to this in a second, but algebraically, you really only have one good choice. And that is this. I actually hope you see this. I would say you've missed something in your algebra knowledge if you don't see this, don't already see this. I'm looking at this one right here because of that x right there. That x is not hard to solve for. All I have to do is add the y squared to the other side, add the 4y to the other side, subtract 6, and I can solve that for x. Why am I doing that? Why is that cool? Because I can now take this and plug it in up here, there, and there. And then I will no longer have 2 equations, 2 unknowns, but by putting them together, I'll have 1 equation, 1 unknown. Now I could have solved this top one. Would you agree with this? I could have also solved this top one pretty easily for y. It wouldn't have been very easy to solve for x since there's an x and an x squared, but I would have had to divide by 2 and then I would have had fractions. And so I could have solved that one for y, but this one here was much better because it's just x. So let's see, what does that give me then? So I have x squared, but x is now y squared plus 4y minus 6, but it's squared, and then minus 20 times x, but x is now replaced with y squared plus 4y minus 6. And then I have a minus 2y, which I'm fine with, and I have a plus 80, which I'm fine with, and then equals 0. And so look, 1 equation, 1 unknown. That's algebra you should know. But it's a horrifying business because when I square this, remember that doesn't mean square just each term individually. I got to multiply everything times everything and toward not screwing this up. If I say I am squaring this, again, I'm going to go a little too fast and hopefully not screw up, but I got to think everything times everything here. So y squared times y squared is y to the 4th. That's plus 4y cubed plus another 4y cubed for a total of 8 of them. So that's the dangerous part. Try to make sure I got all of them. And then let's see, y squared terms. I have minus 6y squared minus another 6y squared, which is minus 12. And then 4y times 4y is another, is a 16y squared. So I have 16 minus 12. I think that's 4y squareds. Ooh, that's dangerous. And then minus 24y minus 24y, and then minus 6 times minus 6. I think I got that right, but woo, I'm really not sure about that. And then minus 20 times y squared, and minus 20 times 4y, and minus 20 times minus 6, and then minus 2y plus 80. So you have 8y cubes. I'm kind of marking everything off. And then I got y squareds, 4 of them, minus 20 of them. That's it. So that's minus 16 of them, 18 of them. No, 16. And then y terms, minus 48, minus 80, minus 2. So what is that? Minus 50 and minus 80, minus 130. And then constants, 36, that's 156, plus 80 is 236, I think. I don't trust that. Double check. 36 plus 120 plus 80. Yeah, 236. So I'm a little concerned I screwed that up and went too fast, but again, from algebra, what are your thoughts on solving that equation? One of them should be painful. But how many answers is this going to have? How many y values are there in that problem that could be possible? And your algebra people should have a better answer for that than most. You should know, just like a squared equation has 2 answers, cubed equations have 3, fourth equations have 4. There could be 4 answers. Now remember, they can be repeated. So you could have 2 3s, and so they aren't actually unique. And some can even be imaginary, but this could have as many as 4 answers. Now think back to your graph. There actually was 4 answers. This is where they're coming from. In other words, if we could solve this equation right here, we would have probably the 4 y values for what looked on the graph to be like the 4 critical points. But how do you solve this? Well, you can't. I mean, if somebody made this up canned and really nice for you, then you could factor it. But you'd have to graph to cheat to even factor it. So it'd be very hard to factor into 4. I mean, it'd be nice if it was like y minus 2 times y plus 7 times y minus 9 times y plus 8. Be nice if it did that, but that'd be kind of unlikely. And maybe this one does because I made it up for you, but I can't remember. But you kind of got to cheat to solve these anyway. And so the easiest way to solve it would be by graphing. If you graph this, and you'd have to sort of think of it as this. You'd almost have to rework it as y equals and think of it as x to the 4th. I mean, yeah, I guess that's not totally true. You could just go into Desmos and do it, but I guess I'll just finish this way. If I thought of this as just sticking it in a graphing calculator, a normal graphing calculator, if I graphed that, then I would be looking for the zeros of the graph, which is of course code for, y equals 0, right? Because I'm looking for x-intercepts, because graphing this, there was never, 2 letters in it, but because I stuck one in there, I'm really looking for when y is 0, which of course means where it crosses the x-axis. That's what zeros are. So if I graph that in my graphing calculator, I could kind of get all of those, and maybe I'd be lucky. As I said, they'd all be whole numbers. So just to go reasonably slowly, I'm going to go ahead and stick this into Desmos just to do it once kind of slowly, and also just to give you time to think and process and all of that. So if I say y equals x raised to the 4th plus 8x cubed. Please tell me if you happen to see any screw ups that I did algebraically, because I did go way fast. But the graph is going to tell us here in just a second whether we got this right. Minus 16x squared minus 130x, because it should match what we saw a second ago. That's the point. Plus 236. So bam, 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 bam. So there's my 4 solutions. And notice, and again, this is a little kind of mind blowing, but it's like those are X values, but you know, for us, those were actually Y values. There's my Y values. So what I'm hoping if I go to the graph is that the graph kind of vindicates that that looks like one of those did have a Y value of 3 and one of them is 1.9 and so on and so forth. Let's see, which way do I want to zoom that? It's this way. I want to make a nicer looking graph, so just so you can actually see the 4th degree nature of this. So I just messed with the window. Now I'm going to go back and pop all of those back in there. This is where Desmos really shines. Take a picture of that. Stick it back over in our notes. Good enough. So those are my Y values. So to put them in order, I guess, negative 6.15, negative 6.75. I guess they're not in order now. 1.9 approximately and 3.01. The question is that match the graph? Negative 6.15, negative 7.5. If I go back up here to our graphs. Yeah, doesn't that one right there? This is a good sign. Let's see, I need a new color. Black. Doesn't that one right there appear to have a Y value of negative 6.15? Wasn't that one of them? And doesn't this one appear like it's at least reasonable that it would have a Y value of negative 6.75? Doesn't that look reasonable? And then what were the other ones? I had a good memory, 1.9, 3.01. So that's a good sign. Do these look reasonable? I would say, well, not so much for this one. What's your thoughts? This one over here looks pretty good. That looks a little above 3, so I'd say 3.01 would be reasonable for that. What's wrong with this one though? Notice it appears to be above 2. What's wrong there? Well, what's wrong is I probably didn't put it in the right spot. Like, did I, do you know exactly where that is? Do you see how it's kind of hard to tell? So I guess apparently it's more like right there, which actually looks pretty reasonable, doesn't it? It looks like it could be there. So in a sense, I must have kind of put it at the wrong spot. So that I went kind of quick, but it looks like I didn't screw it up. It looks like I didn't screw up the algebra. So you see how it's working? Is that kind of cool? So of course, now what? Obviously to find the critical points, it's not enough just to find the Y values. I got to find all the X's that go with them. Does it make sense? This would be a good place to do that. Now remember, you've got, go back to where I was working. I guess I was working right there. I could plug these into any of these 2 equations right here. But doesn't this one feel kind of a particularly good place to plug my Y values in? Like that's where I'm gonna get my X's. So I'm gonna use that one. There. So -6 point, and I rounded that off, but it's pretty close. Yeah, six. I'm going to use the whatever the graph gave me. So I say -6.15 squared plus 4 times -6.15 minus 6, and I got 7.22. So we're going to check these as well in just a second. If I use the second entry command in my calculator, I can just go back and change the 7 to a 1, the 1 to a 7. That was actually 6.749, but I think I'll just leave it 6.75. It's close enough. And I got 12.56 for that one. And then what about 1.9? That was 1.9. I'm going to call it 1.89 just to make it a little more accurate. So what about 1.89? Go replace 6.75 with 1.89. I got 5.13. And finally, 3.01. 3.01, 15.1. I think these are my critical points. And of course, this is the kind of thing I would want you to be able to do on a test, is be able to find these. And so of course, now I'm thinking, you know, is that a match? Like it looked like the Y's were okay, but do those X's agree as well? Ooh, where am I going to put these? For now, I'm just going to stick them right there, but let's see, 7.22 -6.15. Does that fit? Does that work? Oh yeah, it does. Look, there's 6 and there's 8. So that looks right. That looks good. I'm happy with that. And then 12.56 for the next one. This one supposedly is 12.56. Does that look right? Well, there's 12 and that would be 13. So it does look halfway between there. So that looks awesome. So looks like it's working, doesn't it? Let's check them all though. And then 5.13, 1.89. Does this look like 5.13? The answer is, well, there's 4 and there would be 5, and that's really close to 5. Can't really tell what side of 5 it's on, but that looks very reasonable. And finally 3.01 supposedly goes with 15.1. So this is 15.1. I look at that point right there and I think, yep, that also looks good because there's 14 and there's 16. So it's working. Found them. We won't go into this because that's, you know, as far as the book kind of questions go, although I'm giving you my own assignment for this section. But based on the way those arrows are drawn, does it make sense you could choose a point a hair above, a hair below, a hair right, and a hair left of that, and actually determine which way the arrows were going? And see whether this point is kind of a, one that causes a vortex to kind of form. You could calculate that. Now, we have the graph, and so I don't think we need to do that. We can kind of look at the graph and see which ones are behaving that way, but it's kind of cool that you could potentially even algebraically determine what's going on there. So it's kind of a neat idea. I mean, is this kind of cool, kind of powerful? You can sort of see how this really could model weather, and it would be awesome if ahead of time you knew that. And it's also cool that we just proved that there were only 4. There weren't more. That was kind of neat. We didn't necessarily know that. Now we went to all the trouble to do a whole bunch of algebra to like set the 2 systems equal to each other. And then we got it to a 4th degree equation, but then we had to punt and use technology to solve the 4th degree equation anyway. Could we have just solved this clear back here with technology and never done any, never do any algebra, never done algebra? Could I just stick those into Desmos like right as they are? Notice you can't stick those into your graphing calculator because those are implicit equations. They're not solved for y. The top one would be capable of being solved for y. The bottom, you'd have to use the quadratic. You wouldn't want to do that. But, could I just stick those both into Desmos and I would I get all these answers somehow? I don't know. What do you think? I don't know. Let's go find out. So we'll just turn that dude off and we'll type the other ones in. So I have x squared minus 20 x minus 2y plus 80 equals 0. And you should not be surprised to see that as a parabola, because if it was solved for y, it'd be a parabola. And so that's kind of not surprising, I hope. And then the second one is x minus, I wonder if you can predict what this is going to look like. X minus y squared minus 4y plus 6 equals 0. What's going on with that one? Well, remember I messed up the scale of this thing. So I could actually go back and hit the little wrench and say zoom square, kind of fix it. There we go. You should not be surprised that's a sideways parabola. Again, I'm hearkening back to previous algebra knowledge here, but notice the top one was a y and an x squared. That's vertical parabola. And the bottom was an x and a y squared. That's a horizontal parabola. And so, I wonder where these hit each other. Unfortunately, because Desmos won't tell you this. In other words, if I try to click on that, it won't give me those. And that's because the equations are too complicated. It would have done it if they were both y equals equations, it would have worked. So that's kind of disappointing because it's like they're sitting there staring at me. Can you see the answers we just found? Like, look at that one on the left. Can you see that it's a little to the right of 5 and a hair under 2? So like 5.1, 1.9, something like that would be the answer. That's all 4 answers right there staring at us.
It's weird. When I do it on my computer, I'm able to get the 4 answers. They show up when I click on the points. Maybe with
Interesting.
the app,
Got it. So I'm using an app, and so you're saying it did it on regular Desmos. Okay, but it's
yeah,
not
I
doing
had,
it on mine.
I had to click on them first, but then it showed me them.
Sweet. Well, that's really good news because I was actually kind of surprised it wasn't doing that. But yeah, I'm using an app that I downloaded. Like you could download the app I have is on my iPad. You could download it on your phone. So that's good news. So awesome. So, do I want you to do all this algebra? I really don't. I mean, the point of this, you've already done that in the past. And, is it kind of fun to remind yourself how to do it? But again, isn't it disappointing that we ended up with a 4th degree equation, which we really can't solve without technology anyway? So It's like, was that worth the trouble? And the answers weren't whole numbers, which means you weren't going to be able to solve this by factoring. So there really isn't a good way to solve this. You may remember Calc 1, I taught you something called Newton's, I think it was called Newton's method, where that's how your calculator is programmed to find zeros. So your calculator will find those zeros, graphing calculator will find those automatically. You could use Newton's method the long way, which you probably don't remember, but you know, it could be sort of done thanks to calculus. We actually could solve that without being able to factor it, which is really awesome. But my point is I don't have any problem with you just stealing the answer to this based on technology, since we sort of have to rely on that anyway. Thanks for pointing that out, Ben, because that was going to cause us some unnecessary wasted time. So I won't bother to fill those in, but clearly that's the 5.131, but I'm just double checking this. And that one's a little past 15 and a little below, looks like a little below 4. So that must be the 15 3.01. Yeah, I read it wrong. It's like right around 3. Yeah, so it's a little past 15, right around 3. So that takes care of that one. And then this one right here looks to be just to the right of 7. So that's 7.22 negative 6.15. Yeah, that makes sense. And this last one looks just right of like halfway between 12 and 13. Yeah, 12.56 negative 6.75. Cool. So I really can steal these directly off of a graph. I think that does it. So really the two things I want you to be able to find. I want you to be able to draw the phase plane. Obviously that's using technology, and it's got to have arrows in order to be a phase plane. So in the case of what I just showed you, we got to find them ourselves. We got to draw the arrows ourselves, which is kind of cool to be able to do. And then secondly, just being able to find these critical points. That defines the whole show. So just to draw one more kind of phase plane really quickly, just because I have one more example. And the last one was actually 2 parabolas. Does that make sense? The 2 equations were both parabolas. This time though, I have a circle and an ellipse. So what if dy dt was actually x squared minus 8x plus y squared? Right there it tells you it's a circle because you have an x squared plus a y squared. So there's both. So the rest of this is just details. So the graph of that is actually going to be a circle. And I said the second one was an ellipse. Can you recognize this as an ellipse? It's really huge numbers. I have a feeling I made this one. I worked really hard to make this one up. Can you tell right now that's an ellipse? Who can remind us? Why is the top one a circle and the bottom one's an ellipse?
Is it because of the subtraction and the different coefficients in front of it?
It's the different coefficients. They're both positive. Like this is a +1 and this is
Oh,
a +1.
Yeah, I moved a minus sign over in my head.
So those are both the same coefficients. If this had been a 169, that would be a circle as well. They don't have to be ones because remember I could divide both sides by 169. But because their coefficients are different, then that's going to create kind of like a circle with 2 radiuses, like a y radius and an x radius. That's how this could be recognized as an ellipse. if one was positive and one was negative, it'd actually be a hyperbola, which is sort of like, it looks like a parabola going up and a parabola going down. So again, you don't need to know that. It's just kind of cool to jar your brain a little bit. And so can you appreciate this is going to be really hard to solve algebraically? Like if we weren't cheating, this would be really horrible. But let's just take, you go into Desmos really quick and graph both of those. I'm going to do it too on my other screen since Ben said it works better. I'm going to go do Desmos while you're. Remember, you're saying 0 equals all of these things. Plus y squared minus 10y.
Would the critical points be where they intersect?
Yep. And of course, like, why would that be?
Because that's where they're both equal to 0 at the same time.
Exactly right. Keep in mind that the red circle is every single XY point where the top equation is equal to 0, since it was set equal to 0. And the same is true for the blue one. And then where they hit would be where they're both true. And so notice this is still pretty random numbers. Like I thought originally when I looked at it, it's like they must be, you know, nice clean whole numbers, but this is kind of hard to make up. And so there's like, I'm seeing right now that those are going to be critical, important points on our graph, right? Just to have a record of it, I'm going to shoot a quick pic of that. So that's awesome. Picture. So I'm already expecting those critical points, and now I want to create the graph of this. So let's go over here and backspace the whole thing. We said this was rather trying to put into place. So we ended up saying, and remember, it's really important which one goes on top. Like it was, we took the two equations and divided them by each other. Does it matter which one's which? It does. Which one needs to be on top? This is behaving problematically. I've noticed this is really temperamental. Like as I said, you're typing along and you can't really see what you're typing after a point. So you sort of have to type kind of by faith a little bit, or just make sure you're not screwing up. I just looked up and I started doubting that what I typed was correct. Plus, oh, I'm not going to doubt this time. Plus y squared minus 10y minus 23 close parenthesis hit divided by open parenthesis, second equation 169 x squared. It seemed like a minute ago I had the opportunity to troubleshoot it anyway. So 676x plus 9y squared minus 54y. We're getting close now. Minus 764. Close the parenthesis. did double check to see, did that actually type? Did I succeed in typing what I think I typed? Top is good, 169 squared minus 676x. I can change the density of this to be really low so I can see a little better. Plus 9y squared minus 54y. Oh my gosh, I got it right. So the question is, think about the critical points that we just found a second ago, which, you know, you didn't necessarily write down. I'll get it all back together for us in a second, but close, whoa, that's wrong. So I'll just kind of read them out loud, but I got 0.2 and 11. So there's supposedly one, oh, it's off the screen. That's kind of good to know. So my Y max needs to be higher than 10. So if I take it up to 20, is that a good idea? This is kind of hard to see. Changing this to try to figure out. I can't really see these. So there's one really close to the y-axis. Just trying to get where I can kind of see them all. So notice how this doesn't stand out near as much as the last one did. Like I'm really not seeing any. Are you? Like as I look at it, I'm kind of thinking I don't really see any. There was something on here, change this. If you screw something up, there was like a reset. If anything messes up, hit the reset button to store things to default. Where's reset? Is it that? Is it that? Is it that? Somebody rescue us. Where's reset? Is it that? No. Can zoom in, zoom out. I'm just clicking random buttons. Just feeling like I need a different window somehow. That's probably reset right there.
Maybe it's the home button.
Tried that a second ago and it seemed like I was thinking it was going to take me back to 5 and -5, but it didn't do it. So I mean, I see wonky happening down here. There supposedly is something happening here. I'm not really seeing it. But this is kind of good. Okay, let's just pick one for one example. So one of them was at -0.8, -1.1. So would you agree that's like right over here? And I'm looking at that thinking, I'm not seeing that, right? So the question is, if I zoomed in on that, so it was at -0.8 for X. So that means if I went from -2 to like 0, that would be squarish. And then it was at -1 for Y. So if I went again, -2 up to 0, the question is if I zoomed in on that somehow, would I be able to see it? And let's see, I'm going to take my cursor to the point. It was supposed to be -0.84 negative 1.1. So negative 0.84, negative 1.1. So right here, see, I'm not really seeing anything there. What's going on? Does the density make a difference? If I chill out the density. One of the things that's kind of cool about this, I mean, I think is notice how it was sort of more important to do the algebra. There's a couple of places I'm stopping it, like right here at that density, and I can see, yeah, there could be something weird going on right there, but notice it's still not obvious. And there's part of me that kind of is happy to see that because it's like I needed the algebra to find it. I don't know if I would have found it if it wasn't for the algebra. So it's kind of hard for me to tell. I mean, isn't that kind of interesting? I don't know. Let's go look at another one of them just for the heck of it and see if we see anything over there. So there was another one at 3.96, 12.8, so roughly 4 and 12.8. So if I go not an x of 4, but an x of 3 and an x of 5 to be on both sides of 4. And then the y value is 12.8, roughly 13. So if I go from 12 to 14. So there's supposedly one right in there somewhere. Again, it was at 4, 12.8. Roughly in the middle of that somewhere. Again, I find myself thinking, I don't know, I'm not seeing it. What am I doing wrong? What if I back these out 3 in every direction? Does that help? Going out 3 in both directions. Does that somehow help me see it? Notice I'm seeing some interesting things now for sort of the first time, but I see a lot of swirls and curls. But again, the point is actually at 4, 12.8. So that would be right about here. Not really seeing that. Now, 2 things. One is, thank God for algebra because there's something important there. And if it wasn't for algebra, I wouldn't be able to find it. The other possibility is, well, I did this wrong. I typed something in wrong, got a sign wrong, whatever, you know, it kind of could be anything. My original graph wasn't right. I typed something in wrong. I'm staring at that right now. Double checking my 2 graphs, x squared minus 10y minus. Oh, that was wrong. That was supposed to be 23. That seems like a pretty small mistake, though. Maybe it'd make a difference. Anyway, we're over time, but wow, I got to be careful there. There's 2 points to find. So I'll stick these 2 in the notes and, you know, add a couple before I post it. I'll just add a couple of thoughts to this, but that's the idea. Notice it's kind of quick. I mean, this isn't a very satisfying one, but it's pretty quick. Your ability to ascertain this and so forth. So the only other thing I would have, you know, because we kind of ran out of time, I'd like to have graphed it and, you know, put all the arrows in it. That's what I was planning on doing, but, you know, we just kind of ran into some issues. So plan tomorrow is to review, and we'll look at that together and take a final the next time. The only other thing I want to remind you of is if you go into My Open Math and log in and go to our class and go to homework. You got to go here to find this. There's homework scans. I showed you this on Thursday. There's homework scans from the 8th edition. And the 5.4 worksheet is right there, bam. So the reason I made my own problems up is because I wanted these to come out, good. So notice this is a line and x squared, 2y squared. This is a line running into an ellipse. Maybe if you picture that in your mind, you think, oh, that'll have 2 critical points. A line would hit an ellipse twice. So this is only gonna have 2 critical points. This is a parabola and a line. Yeah, parabola and a line, that'd be also 2 points. This is a parabola and a parabola. Well, maybe parabolas and parabolas hit each other 4 times. It looks to me like, so I can think about that. So find the critical points, use software to produce a phase plane. And I said, add your own arrows. So you're going to need to, print that. You're going to have to, or scan it or take a picture of it and write it. But you got to add your own arrows onto that, or perhaps you'll find a better computer software site that'll actually produce the arrows automatically. If you do, then use that. That's fine. But you got to get me that somehow, so I don't know, is that a printer or is that scanning it? But you got to be able to add the arrows yourself. Otherwise you're not really done. On a test, if I gave you a question like this, I would give you the phase plane and then you'd be, doing a couple dx dt calculations to figure out where all the arrows were and kind of adding some of those in yourself. So we will probably look at that assignment a little bit tomorrow. Let's see, when is that assignment due? It's due at the end of tomorrow. So you don't have to be due during class tomorrow, but you got to be due at the end of tomorrow. So you might start the day, just looking at how did you do with this and make sense of it. These are just better questions that were in the book. So that's why I made my own up. Okay. That's good enough for now. Stay after if you like. Otherwise, I'll see you tomorrow.
Okay, thanks, Doug.
See you tomorrow, Doug.
Thank you all.